Now I want to talk about key-value memory networks for directly reading documents. This article in 2016. So what is the problem of knowledge bases? Unfortunately, knowledge bases have intrinsic limitations such as their inevitable incompleteness and fixed schemas and cannot support all varieties of answers. So the idea of key-value networks is that it makes reading documents more viable by utilizing different encodings in the addressing and output stages. So if you look at the brain, the memory is first you encode and then finally you retrieve it. Encode and then store and then you retrieve it. This is how it is done in your brain. And I have written an article in Medium about this important thing, that even reasoning is a kind of memory process, a mental process. So in this work, they propose key-value networks and new neural networks that generalizes original memory network. In the previous lectures, I explained memory networks. So they say that it generalizes memory network. It's obvious because they introduce the key and the value matrices as well. Just like transformer architecture, just like neural Turing machine, that in neural Turing machine, they have a controller that generates your key. So this is another source of variability and design. And so this key-value memory neural network performs question answering by first storing facts. We store facts in our memory, key-value structure memory, before reasoning on them in order to predict an answer. The memory is designed so that the model learns to use keys to address relevant memories with respect to the question, whose corresponding values are subsequently returned. They are a generalization of the way contexts are stored in memory. So the lookup stage is based on the key memory, while the reading is based on the value memory. So it gives both greater flexibility for practitioner to encode prior knowledge about their task, also more effective power in the model of non-trivial transforms between key and values. And the key should be designed with features to help match it to the question. And the values should be designed with features to help match it with response. So we have a question and we have an answer. So the keys are, we give question and it generates a key. So it's more close to the question. On the other hand, if you want to generate an answer, first you need to generate the value. And from value, you generate the answer. So value is here, key is here, and the query is here. And this is your model. And this is your model. So the key value memory networks, first you do question embedding. And then you have some keys. So depending on those keys, which one is more relevant, and depending on your answers, some of the values are more relevant. So you augment, concatenate all of them together. You merge all of these ideas together. So what is the key hashing? Because the addressing and reading of the memory needs 3 steps. Step 1 is key hashing. The question can be used to pre-select a small subset of possibly large array. This is done using an inverted index that finds a subset of memories. By the way, Professor Christopher Manning has explained inverted index in the context of information retrieval on YouTube, and you can watch that beautiful video. And it's a playlist that he teaches information retrieval in a very beautiful way. So this is done using an inverted index that finds a subset of memories of size n, where the key shares at least one word with the question with frequency less than 1000. The second stage is that during addressing, each candidate memory is assigned a relevance probability by comparing the question to each key. So we compare each question to each key, and then we have a relevance probability. And in the third stage, we have value reading, because now that we want to know the output, the final reading, the values are memories are read by taking their weighted sum using the addressing probabilities. So this is the probability, the relevance probability that I explained here. This is the relevance probability. It shows that the relevance of each memory, because each key is relevant to a question. So this is the probability that each key is relevant to the question and this question itself. And combining them, the memory access is conducted by the controller using this question. So question is written like this as a query. This is a query. So X is the question, Q is the query. So from question we go to the query, just like any other article. And after receiving the results output, we just add it with the question, with the query, and gives you the updated query. The memory access is then repeated, only the addressing and reading steps, but not using a different matrix on each hop. The key addressing equation is transformed accordingly to use the updated query. The motivation for this is that the new evidence can be combined in the query to focus on and retrieve more pertinent information in subsequent accesses. Finally, after a fixed number of edge hops, the resulting state of the controller is used to compute a final prediction over possible outputs. So this is the answer. So yi are possible candidate outputs. For example, all entities in your knowledge base, or all possible candidate answer sentences. And this B matrix can also be constrained to be identical to A, and the whole network is trained end-to-end, just like the previous lecture that was end-to-end. And the model learns to perform the iterative accesses to output the desired target A. And this is our desired target. And then backpropagation and stochastic gradient descent are used to learn the matrices A, B, R1, RH. To obtain the standard end-to-end memory network, one can simply set the key and value to be the same for all memories. That's why it is the generalization of my previous lecture. This lecture is the generalization of the previous lecture. And previous lecture was the generalization of previous lecture of that. Hashing was not used in that paper, but is important for computational efficiency for large memory sizes. There are a variety of ways to employ key-value memories that can have important effect on overall performance. The ability to encode prior knowledge in this way is an important component of key-value memory networks. And we are free to define those phi for query, answer, keys, and values. We now describe the several possible variants of phi that we try in their experiment. For simplicity, they kept phi x and phi y fixed as a bag of word representation. For example, they used knowledge-based triple or at the sentence level for representing a document, one can split it into sentences. Or window-level documents are split into windows of W words. Or window and title. And they compared different memory representation, window, label, and they have different performance. But this one has higher performance if you combine it by center, encoding, and title.